Welcome. The topic we will be discussing in this lecture is process control block. Each process is represented in the operating system by a process control block. So basically, process control block contains all information about a particular process. So it includes all state information about a particular process. So process control block is also called as task control block. So what this process control block contains? It includes several information. So first it includes something called as process state. So in the last lecture, we have discussed about process state. That is, a process can be in any one of the 5 states during its lifetime. So currently, what is the state? So that will be represented through process state. Okay, like whether it is in the a new state or ready state or running state or waiting state or it is in the blocked state. And then the PCB also includes program counter, which contains the address of the next instruction to be executed. That is, it includes the value of the program counter, which contains the address of the next instruction to be executed. Then PCB also includes the values of the CPU registers. So primarily it includes values of three types of CPU registers, which are called as accumulators, index registers, and general purpose registers. So basically it includes the values of three types of registers. One is accumulator, the other one is index register, and the other one is general purpose registers. Okay, so let us understand what these three registers are. So first let me start with accumulator. Accumulator is a accumulator is a special register. Accumulator is a special purpose register which is used by the processor to store the intermediate results of arithmetic and logical operation. Accumulator is a special purpose register in the CPU which is used by the processor to store the intermediate results of arithmetic and logical operation. So basically this corresponds to the assembly language code, because you cannot, if you want to directly program and processor, you should use assembly language, right? So if there is an instruction something like this, add b, okay. So let us see, there is an instruction add b, and before that say b contains the value 10. Let us assume b contains the value 10. So what does it mean, this instruction add b? What it means, b should be added with what? So B should be added with what, in the sense, if no other register is provided, it means B should be added with accumulator. Okay. So if accumulator already contains 5, if accumulator already contains 5, then this 10 will be, the B value 10 will be added with 5 and the result will be stored in accumulator. So the new value of accumulator will become 15. Okay, new value of accumulator will become 15. Okay, next if you give an instruction like multiply B, again what it will do, the content of B will be multiplied with the content of accumulator and the new value will be stored in accumulator. So now the content of B is 10, content of accumulator is 15, this will be, so B content 10 will be multiplied with 50 and the result will be stored in, again, accumulator itself. So the new value of accumulator will become 150. Okay. So this is how accumulator is used as an intermediate place to store the results of arithmetic and logical operation. And coming to index registers are used mainly when you are working with arrays. So when you are working with arrays, index register will act as a pointer to move from one index location of the array to the next index location. So initially index location will point to the 0th location of the array. Okay. So along with index register, when you are accessing an array, you will be also using another register which is called as base register, base pointer. So this base pointer, say there is an array with k locations. So initially the base pointer will point to the first location. This base pointer will point to the first location. Let us assume the starting address is 3500. If the starting address is 3500, then the base pointer will contain the value 3500. Okay, then the base pointer will also hold the value 3500. So base pointer will always have the starting address of the array, whereas the index register will keep on change. Initially the index register, let us assume this is the index register. So index register currently it will contain the value 0. Okay, it will contain the value 0. So if the program want to access this array, it will access all locations one by one, right? So first it will access the 0th location. So for that, what it will do in the sense, it will add the content of the base pointer with the content of the index register. This both will be added. So when you add, what you get, 3500 plus 0 is 3500. So whatever the content here, it will be retrieved. So if the content is x1 will be retrieved. Okay. Then index register will be incremented by 1. Okay. So after retrieving x1, index register will be incremented by 1. So no more, now it is 0, it becomes 1. So next time when you add, when the program adds 3500 plus index register, it is 3501, which refers to this location. Okay. So this location may contain a value x2. So the program now can access the next value, which is x2. So after accessing x2, again it will increment the index register to 1, so it will become 2. So now it can access the next value, which is x3. So this process continues, so on and so forth. So this is how index registers are used to access the next location of the array. Okay, so this is the usage of index register. And then we have general purpose registers. General purpose registers are used to perform normal arithmetic or logical operations. So if you want to perform any arithmetic operation between two values, then you can just store the two values in those two registers, and you can just use the general purpose register for performing the operation. Say for example, if I perform something like this, add b comma h. Let us assume b is a general purpose register and h is a general purpose register. So what it will do in the sense, the content of b will be added with h and the result will be stored in b. Okay. So this type of, so general purpose registers are used to perform this type of operations. So these are the different CPU registers. So the values of the CPU registers are also part of PCB, program control block. Okay. And another important thing is, whenever there is an interrupt, what happens in the sense, the the process will push the entire content of PCB into stack. The process will push the entire content of PCB into stack. So if the current process running is P0, and if P0 has to service some interrupt, then it will push the content of PCB of P0 into stack. Okay. So after pushing PCB to stack, then it will go to that particular interrupt service routine. It will execute the interrupt service routine. After the interrupt service routine is finished executing, then once again it will come back. Once again it has to come back and continue with particular process P0, because P0 has not finished. In between it executed the interrupt. So for that, how it will come back? It has to know the state of the process. So it will pop the content of PCB from stack, so that it know the full information about the process, and then it will continue from where it left. Okay. So uh, so this is how PCB is used. Okay. And the other information PCB contains includes CPU scheduling information. So this CPU scheduling information, it includes the priority of a particular process. So when there are more than one process in the memory, different process may have different priority. Maybe some process may have highest priority. So even though that process may be coming late, or it is available in the queue at a different location, not in the first location, it may be given a priority to be executed first. So process may have priority, and also there are different scheduling algorithms available, which we will be discussing in the coming classes. So what scheduling algorithm it is using, all those are part of CPU scheduling information. Then we have something called as memory management information. So this memory management information, it includes uh, details like what is the range or what is the limit of memory the particular process can access. So each process will occupy some amount of memory. So if there is a process P naught, it will be given access to some part of memory. So it means it can access only this much memory. It cannot access beyond that. So how it is achieved in the sense, for that the operating system uses two registers. One is called as base register. One is called as base register. The base register will contain the starting address of the memory for this particular process. Okay. So say the starting address for this particular process is 2000. So if base register contains the value 2000, then it means that it can start accessing from the location 2000. But how long it can access? From 2000 to which location it can access? So that is specified through another register which is called as limit register. That is specified through another register which is called as limit register. So if limit register contains 200, so base registers contains 2000, whereas limit register contains 200. So it means that it can access 200 locations starting from 2000. Okay, the basic maximum it can access only 200 location, and its starting location is 2000. So its starting address is 2000, and how much locations it can access? It can access only 200 locations. So it means it can access from 2000 to 2199 location. So this last location will be 2199. It cannot access anything beyond 2199. Okay. So this information is a part of memory management information. Similarly, memory management information also includes something called as page table. A page table is something which maps the logical address space with the physical address. So logical address is something which is used by the virtual memory. Okay. So virtual memory provides an illusion to the user as if you have an unlimited memory. But in reality, that is not the case. So what virtual memory provides is a logical memory. So there is something called as page table, which maps the logical address space with the physical address. So that is also, the page table detail is also part of memory management information. Okay. We'll discuss about page table later as a separate topic, but this is just for your information. And next, the PCB also contains accounting information. The accounting information includes details like how much CPU time it has used so far, and each time when this particular process gets the CPU, uh, how much slice of time will be given by the CPU. Okay, that is, CPU will allocate how much time for this particular process, either 5 millisecond or 10 millisecond, what time it will allocate, and what is the process number. Okay, and other details. Okay, other, basically it is something like a log details. And then we have something called as IO status information, which includes the list of IO devices allocated to this process, and also it includes details like list of the files this particular process can access. Right. So, so this is the pictorial representation of PCB. It includes process state, process number, program counter, different registers, memory limits, list of IO devices, and list of open files. Okay. And this particular diagram shows how the PCB content is stored into stack when the process is uh, going from one process, when the control is switching from one process to another process. Okay, so here the scenario is there are two processes, P0 and P1. Okay, so initially the P0 is executing for some time, and then it is switching to P1. Okay, and then it is switching to P1, and it is executing P1 for some time, and again it is switching back to P0. Okay, this is the scenario. So how it is happening? So initially P0 is executing. So P0 has its own PCB, which we call it as PCB 0, which we call it as PCB 0. At this point of time, the process P0 want to execute P1. So what it does in the sense, it stores the PCB 0 into stack. It pushes PCB 0 into stack. Okay. and then it should execute process 1. So process 1 will have its own PCB, which is called as PCB1. So it loads PCB1. So it loads PCB1 because it has to now execute P1. Okay. So it loads PCB1 and it starts executing process 1. Okay. Again, after executing process 1 for a certain period of time, again it want to stop executing PCB1, I mean process 1, and it want to execute process 0. So what it does in the sense, currently it is executing process 1. So it stores the content of PCB1 into stack, which is the state of process 1. And again it want to execute process 0. So it loads PCB 0, it loads PCB 0 from stack. Either you can call it as load or pop, and now it knows the state of process 0 and it starts executing process 0. Okay. So this is a key feature how PCB helps in switching from one process to another process. So whenever you switch from one process to another process, you load the particular process from which you want to you store the particular process from which you want to switch into stack, and load the process from where you want to switch from the stack, load to the active memory and start executing it. Okay, fine. So whenever there is a switch happens, this switch also you can call it as either interrupt or system call. Okay, whenever you want to move from P0 to P1, so that is an interrupt or a system call. Similarly, again when you want to move from P2 to P1, that is also an interrupt or a system call. So this is how CPU switch from one process to another process. Okay. So far we are discussing about process. Process are normally assumed to be single thread of execution. That is, each process, the operating system may be running multiple processes, but each process is generally considered to be having only one thread. But that may not be all the cases. In modern operating system, a process can also have multiple threads. The process can also have multiple threads. For example, when you are executing the word processor application, it can also read your text, whatever you are typing, and also in the background, it can check for spell check. So in that case, there are multiple threads are running. Okay. So if there are multiple threads in the process, then the PCB process control block should provide features to store information about these threads also. Okay, and also it may need to provide a feature to include multiple program counters. So that's it about process control block. So we have discussed what is a process control block and what the process control block contains. And we have discussed how the processor switches from one process to another process with an example, like how it pushes or saves the PCB into stack, and how it pops or reloads when it want to go to a new process. and and if multi-threading features to be included, then the PCB should also support that. The PCB also should support to provide details of thread, and it should support for to include details of multiple program counters. Okay, so we'll stop with this. Thank you.